It often begins in the quiet. Perhaps you are in a familiar room late at night. The sounds of the day have faded. The machines are quiet, the voices are asleep. There is only the steady rhythm of your own breathing and the deep, profound stillness of the night. You look out the window past your own reflection and into the dark. The sky on a clear night is an ocean of black. It is a peaceful darkness, a velvet expanse that has looked down on humanity for its entire existence. It feels ancient, permanent and remote. We feel the solid ground beneath our feet and see this untouchable canopy above. We stand on what feels like the shore of an infinite, unchanging sea. This is the shore of the cosmic ocean. If you are fortunate, if you are far from the electric haze of the cities, your eyes adjust to the darkness, and you see it. Stretching from one horizon to the other is a faint luminous path. It is not uniform, it is mottled with dark patches thicker, in some places thinner in others. It looks like a ribbon of spilled milk, a cloud of diamond dust, or a glowing celestial river. For millennia we gave this sight names drawn from our own lives. The ancient Greeks told a story of a goddess Hera pushing away the infant Heracles, and her divine milk sprayed across the heavens. They called it the Galaxias Kyklos, the Milky Circle. In China it was the Silver River separating two lovers. In the high deserts of the Andes it was the celestial counterpart to their own great river. To almost every culture that looked up it was a road, a river, or a pathway for the gods. It is beautiful as a myth, but the reality is so much more staggering it can stop the heart. That shimmering band of light, the Milky Way, is not a cloud in our atmosphere. It is not a river. It is not a supernatural scene on the doom of the east. It is us. That faint light is the combined glow of stars. Not thousands, not millions, but billions of stars. They are so far away and so densely packed in that direction that our naked eyes cannot separate them into individual points. They blur, resolving only into a collective pearlescent glow. The reason it appears as a band is perhaps the greatest shift in human perspective ever achieved. We are not looking at the Milky Way, we are looking from it. Our home is a vast, flat, spinning disk of stars, gas and dust. Think of it as an immense city of light shaped like a thin dinner plate or a vinyl record. Our star, the Sun, and our planet, the Earth, are located inside this disk about 2/3 of the way out from the centre. When we look up at the night sky, away from that glowing band, we are looking out of the top or bottom of the plate. The sky seems darker, emptier, because we are looking through the thinnest part of the disk. But when we look toward that band, we are looking the long way through the dense, crowded plane of the disk itself. We are looking edge-on through tens of thousands of light years of our own city. We are seeing the structure of our own home from the inside. This structure, this island universe, has a name. We call it a galaxy. The word itself, galaxy, comes from gala, the Greek word for milk. Our home is the Milky Way galaxy. It is an almost incomprehensibly vast system. If our sun were the size of a single grain of sand, our galaxy would be a spinning continent wider than a city. It contains perhaps 400 billion stars, 400 billion suns. Many of them likely have their own planets, their own worlds. This realization is profound. We are not the center of everything. We are inhabitants of a small, fragile blue planet orbiting a very average star lost in a forgotten corner of a city of 400 billion suns. We are a single speck of dust in an immense forest of light. But what then are the familiar pictures we see in the sky? What about the patterns we have been taught since childhood? We see Orion the hunter with his belt and sword. We see the Big Dipper pointing the way to the North Star. These constellations are the landmarks of our night sky. They are the familiar trees right in front of us in this cosmic forest. They are our immediate neighbours, but they too are an illusion. We see them as flat connect-the-dots pictures as if they were punched into a black ceiling. The reality is that the stars in a single constellation are not connected at all. They are scattered through three-dimensional space at vastly different distances from us. The star at the shoulder of Orion might be 500 light-years away, while the star at his knee might be over 800 light-years away. They have no physical relationship to one another. They only form the pattern of a hunter from one single vantage point in the entire galaxy ours. From any other star system, the constellations would be unrecognizable. They are the streetlights of our local neighborhood, but the band of the Milky Way that is the glow of the entire metropolis. We stand on the shore. We have given names to the few shells at our feet and the nearest waves. We have mapped the patterns of the constellations and told stories about the great river of light. But we are only just beginning to understand the blackness is not empty. It is an ocean, and it is full, and so we drift. We have found our place in the cosmic address, a single point of light within a supercluster. But now it is time to come home, to truly understand the place we live, not just the Earth or the solar system, but our grand spinning island in the void, the Milky Way galaxy. This is our house, but it's a strange house to understand. Why? Because we have never ever seen it from the outside. We are trapped inside. All the beautiful pictures you have seen of a majestic swirling spiral with glowing arms, those are artists' drawings. They are reconstructions based on evidence, or they are pictures of other galaxies like Andromeda that we think our own home resembles. So how do we map a house we can't leave? How do we know its shape? Imagine you are standing in the middle of a massive, bustling city square during a holiday celebration. It's shoulder to shoulder with people. You are not allowed to move from your tiny spot, and you are blindfolded. Now try to draw a map of the entire city. It seems impossible. This is the challenge that faced astronomers. When we look up, we are in that crowd. The crowd is made of countless stars, but even more troublesome, it is made of vast, dark clouds of dust. This dust is like a thick fog that blocks our view. We cannot see the center of our own galaxy with a normal telescope. It is completely hidden. So how did we do it? First, we noticed a clue. On a very dark night, far from city lights, you can see a hazy, beautiful band of light stretching across the sky. This is the Milky Way. For thousands of years, people told stories about this river of light, but astronomers realized what it was the city. We were seeing it from the inside. The fact that it's a band means that the city is flat like a giant pancake or a disc. We are looking out through the thickness of the pancake, but we still couldn't see the center or the shape. To do that, we had to cheat. We had to find a way to see through the dust. It turns out that light comes in many forms. The light our eyes can see is just one tiny part. There is other light like infrared light, which is the light of heat. This kind of light can pass right through the dust like an X-ray passing through your skin. When we built telescopes that could see in infrared, the city was suddenly revealed. The fog vanished. We could see the bright, crowded center and the shapes of the stars. We also used radio waves. We didn't just look at the galaxy, we listened to it. The most common thing in the entire galaxy is hydrogen gas, and this hydrogen drifting in space gives off a very specific, very faint radio signal. It hums at a wavelength of 21 centimeters. By tuning our radio telescopes to this song, we could map the hydrogen, and we could do something even more clever. We could tell if the gas was moving toward us or away from us. When it moves away, its pitch is lower. When it moves toward us, its pitch is higher. This is how we discovered the arms. We mapped the song of the hydrogen gas and found that it was organized into vast, spinning spiral patterns. We were standing in a crowd blindfolded, but we mapped the city by listening to its hum. So what does this map show? What are the parts of our galactic home? Our house, the Milky Way, has three main parts. The first part is where we live. It's called the galactic disk. This is the pancake, the flat spinning record. It is huge. It is about 100,000 light years from one side to the other. That number is so large it's almost meaningless. It means that light, the fastest thing in the universe, takes 100,000 years to travel from one edge of our city to the other. Our sun is just one of about 400 billion stars in this disk. We live out in the suburbs about 2/3 of the way from the center. The most famous features of the disk are the spiral arms. These are the bright, beautiful lanes winding their way around the center. We live in a small partial arm called the Orion Spur, tucked between the larger Sagittarius and Perseus arms. But here is a beautiful, strange secret. The spiral arms are not things. They are not solid structures. A star is not in the Perseus arm forever. The best way to think of them is as traffic jams. Imagine a highway with a patch of slow-moving traffic. The cars, which are the stars and the gas clouds, are always moving. They travel around the galaxy in their own orbits. But when they reach a certain area, this density wave, they have to slow down. They get bunched up together in the traffic jam. Then they push through it and speed up again on the other side. The jam itself, the pattern of slow traffic, stays in one place or moves very slowly, but the individual stars are just passing through. So why are these arms so bright? Why do they glitter? It's because of the gas. When a giant cold cloud of hydrogen gas drifts into this cosmic traffic jam, it gets squeezed. It's compressed by the traffic. And this compression, this squeezing, is what triggers the birth of new stars. The cloud collapses under its own gravity and fragments into thousands of new hot, brilliant blue stars. The spiral arms are bright because they are the galaxy's stellar nurseries. They are where the action is. They are glittering with the light of brand new suns. Our own sun was probably born in an arm like this 4.5 billion years ago. Now let's travel. Let's move from our suburban home and fly toward the center. As we get closer, the stars get more and more crowded. We are leaving the flat disk and entering the second part of our home, the galactic bulge. If the disk is a flat pancake, the bulge is like a grapefruit stuck in the middle. It's a dense, bright, spherical swarm of stars. This is the downtown core of the galaxy. It is ancient. The stars here are different from the ones in the arms. They are not the young, hot blue stars. These are the veterans. They are old. Many are 10 billion years old, nearly as old as the galaxy itself. Because they are old, they have cooled down and they glow in the warm, soft colours of yellow and red. Their orbits are not the calm, orderly circles we see in the disk. The stars in the bulge swarm around the centre like a cloud of angry bees moving in all directions in fast, chaotic orbits. And at the very centre of this swarm, at the exact heart of our galaxy, lies a monster. A supermassive black hole which we call Sagittarius A star. It has the mass of 4 million suns all crushed into a single invisible point. It is the anchor. It is the drain around which the entire 100,000 light-year city of stars is swirling. Now let's zoom out. Let's pull our view back past the bright centre, past the spinning disk where we live. Let's keep going until the entire galaxy is just a bright pinwheel in the distance. We are now in the third part of the house, the galactic halo. This is the galaxy's atmosphere. It is a vast, empty, spherical aura that surrounds the entire disk. It's like a ghostly bubble, and the disk is just a flat structure inside of it. The halo is almost empty, but not quite. Drifting through this vast darkness are the oldest residents of the Milky Way. They are called globular clusters. If the spiral arms are new nurseries, globular clusters are cosmic retirement homes. They are ancient tight balls of stars. Each one is a small compact city of its own containing hundreds of thousands of stars, all born at the same time at the very, very beginning of the galaxy's life. These clusters are like fossils. They orbit far above and far below the disk, moving on their own long, slow paths. They are the ghosts of the galaxy's birth. And this halo is also where the biggest mystery lies. The stars and the clusters we can see, they are not enough. The galaxy is spinning so fast that it should fly apart. The stars on the outer edge are moving too quickly. By all of our calculations, they should be flung off into space. Something must be holding it all together. Some invisible gravity. We now know that the vast majority of our galaxy, perhaps 90% of its mass, is made of a substance we cannot see. We call it the dark matter. The halo is filled with this invisible scaffolding. Our galaxy, our home, is built inside an invisible structure that we are only just beginning to understand. So we have this structure, a central bulge, a flat disk, and a giant halo. It's easy to picture it as a static crystal-like object, a finished thing. But it is not. The galaxy is a living, breathing ecosystem. It has weather. The space between the stars is not empty. It's filled with what we call the interstellar medium. This is the air of the galaxy. It's an incredibly thin mix of gas, mostly hydrogen, and tiny particles of dust like soot. This air is constantly in subtle motion. Stars are like fans. Our own sun breathes out a constant stream of particles called the solar wind, which creates a breeze. Some giant stars create powerful winds that are like hurricanes sculpting the gas clouds around them. But the most violent weather of all is a supernova. When a star much, much more massive than our sun ends its life, it doesn't just fade away, it explodes in a single brilliant moment. It can outshine all the other 400 billion stars in the galaxy combined. This explosion sends a shockwave tearing through the interstellar medium. It is a cosmic tsunami, a blast of energy and matter moving at thousands of miles per second. This violence seems like pure destruction, but it is not. It is the engine of life. It is the heart of the great galactic recycling program. You see, when the universe was first born, it contained only hydrogen and helium, the simplest, lightest gases. The iron in your blood, the calcium in your bones, the oxygen you are breathing right push now, it did not exist. It was made. It was forged deep inside the hearts of those giant stars. They spent their lives fusing light elements into heavier ones. Carbon, nitrogen, oxygen, iron. When that star exploded, it did not just die. It delivered. It scattered all those new heavy elements across the galaxy, enriching the interstellar medium. This star stuff, this cosmic ash mixed with the fresh hydrogen clouds. Billions of years later, another shockwave, perhaps from another supernova, squeezed one of these enriched clouds. A new solar system began to form. This time the cloud wasn't just hydrogen, it had iron, it had carbon. It had all the building blocks for rocky planets, for water, for life. The galaxy is not static. It is a giant slow-motion engine. Stars are born from gas. They live, they die, and in their death they return their substance to the galaxy, providing the raw material for the next generation of stars and planets. You are in the most literal sense made of stardust. The atoms that make up your body were not created on Earth. They were forged in the heart of a star that died long before our sun was born. They travelled for light years through the dark, drifted in the spiral arms, and finally came together to form this planet and to form you. Our galaxy is not just a house. It is a parent. It is a living system. And as you fall asleep, feel yourself a part of it. Feel yourself drifting in this grand, beautiful recycling city of light. The great spiral arms of a galaxy are not static, beautiful swirls painted on the blackness of space. They are dynamic, churning rivers of gas and dust waves of compression and creation sweeping through the galactic disk. These arms are where the action is. They are the galaxy's manufacturing districts, and their most active sites are the vast glowing clouds we call nebulae. These are the cosmic nurseries, the maternity wards of the universe. When we look at them, we are witnessing the very beginning of the cycle. Perhaps the most famous is the Orion Nebula, a fuzzy luminous patch visible to the naked eye just below Orion's belt. Through a telescope, it resolves into a breathtaking cavern of glowing gas, primarily hydrogen illuminated from within by a cluster of brilliant newborn stars. These young stars, known as the trapezium, are stellar infants, and their intense ultraviolet radiation is what makes the surrounding gas light up in shades of red, blue and green. It is a region of chaotic, beautiful creation. Even more iconic is the Eagle Nebula. Deep within this cloud of gas lies one of the most famous images ever taken by humanity, the Pillars of Creation. These structures are exactly what their name implies. They are colossal towers of cold interstellar gas and dust standing light years tall. They look like ghostly mountains or dark smokestacks, dips rising against a starry background. They are in reality dense reservoirs of the raw materials for star making. The pillars themselves are being eroded, sculpted by the fierce stellar winds and harsh radiation from a cluster of massive young stars located just outside our view of them. This radiation is evaporating the less dense gas, revealing the much denser clumps hidden within. Inside these dense pockets, shielded from the destructive radiation, gravity is winning. New stars are being born hidden from our sight in their dusty cocoons. The Pillars of Creation show us both birth and destruction happening at the same time. They are a perfect snapshot of the cosmic cycle. So how does this happen? How does a cold, dark cloud of gas ignite and become a star? It all begins with gravity. A nebula is not perfectly uniform. It has regions that are slightly denser than others. Over millions of years, gravity pulls these denser clumps together. As the clump of gas and dust gets more compressed, it begins to spin, flattening into a disk like a spinning pizza dough. At the center of this spinning disk, a dense, hot core forms. This is a protostar, a baby star. This protostar is not yet a true star because it is not powered by nuclear fusion. It glows, but it glows only because it is hot from the friction and pressure of its own gravitational collapse. It is a wannabe star still gathering mass, pulling in more and more gas and dust from the surrounding disk. For this protostar, mass is everything. The core of the protostar continues to crush inward, and the temperature and pressure climb to unimaginable levels. When the temperature at the very center reaches about 10 million degrees Celsius, a critical threshold is crossed. The pressure becomes so intense that individual hydrogen atoms, the simplest and most abundant element, are slammed together with such force that they overcome their natural repulsion and fuse. They merge to create air, create a new element, helium. This is the moment of ignition. This process, nuclear fusion, unleashes a tremendous amount of energy in the form of light and heat. This outward pushing energy finally becomes strong enough to fight back against the inward crush of gravity. The two forces, gravity pulling in, fusion pushing out, reach a perfect stable balance. The collapse stops. A star is born. It switches on and blows away its remaining cocoon of gas and dust, revealing itself to the universe. After its fiery birth, the star settles down for the long, stable adulthood of its life. This phase is known as the main sequence. Our own sun is a main sequence star, and it has been in this stable phase for about 4.5 billion years. It will remain this way for another 5 billion years. During this phase, the star is a model of reliability. It sits in its corner of space, calmly and steadily burning through the massive supply of hydrogen fuel in its core, fusing it into helium. This is the star's prime of life. It is this predictable, long-lasting stability that allows for the possibility of complex systems like planets to form. in the disk of material left orbiting it. And it is this same stability that allows life, once it appears on one of those planets, to have the billions of years it needs to evolve. The calm, steady light of a main sequence star is the engine of life. But this stability cannot last forever. Eventually the fuel begins to run low. Every star, no matter its size, will one day face an energy crisis. What happens next is the most dramatic part of a star's life, and its destiny is determined entirely by one factor: its mass. How much material did it start with? Here the paths of stars diverge dramatically. Let us first follow the path of a low-mass star, a star like our Sun. After billions of years of steady fusion, the hydrogen in the star's core is completely exhausted. It has all been converted to helium ash. The furnace in the center shuts off. Gravity, which has been held at bay for billions of years, now wins. The helium core begins to collapse under its own weight. This collapse, however, heats up the core dramatically. This heat radiates outward to the surrounding layers, heating up a shell of fresh unburned hydrogen around the core. This shell becomes so hot that it ignites with hydrogen fusion. This new shell burning is incredibly intense, far more so than the original core burning. This new furious energy pushes the star's outer layers outward. The star begins to swell, and swell and swell. It expands to hundreds of times its original size, becoming a red giant. It is red because its outer surface has expanded so much that it has cooled down, glowing a dull red instead of a bright yellow-white. It is giant because it is now large enough to swallow the orbits of its inner planets. When our Sun becomes a red giant, it will vaporize Mercury, Venus, and possibly Earth. This phase is unstable. The star's core continues to collapse and heat up until it is finally hot enough, about 100 million degrees, to ignite the helium ash. The helium now begins to fuse into carbon and oxygen. The star has a temporary new lease on life, burning helium in its core, but helium is a less efficient fuel and it runs out quickly. When the helium is gone, the star's core, now made of carbon and oxygen, collapses again. But for a low-mass star, that's the end of the line. It simply isn't massive enough to create the pressures and temperatures needed to fuse carbon. The star becomes highly unstable. Its internal furnace sputters, causing the star to puff its outer layers away in a series of gentle thermal pulses. This material, the star's entire outer atmosphere enriched with the helium and carbon it created, drifts off into space. This expanding cloud of gas is then illuminated by the tiny, intensely hot core left behind. This creates one of the most beautiful and ghostly objects in the cosmos, a planetary nebula. The name is a mistake from early astronomers. They have nothing to do with planets. They are the intricate, colourful, glowing shrouds of dying stars. They look like celestial soap bubbles, cosmic rings, or ethereal butterflies painted across the sky. At the centre of this beautiful structure is the star's corpse. The core, no longer able to produce energy, collapses one final time into an object about the size of Earth. This is a white dwarf. It is one of the densest objects in the universe. A single teaspoon of white dwarf material would weigh several tons. This stellar remnant is no longer a star, it is a cooling ember. It will simply sit in space and radiate away its residual heat for trillions of years, eventually fading into a cold, dark, black dwarf. This is the quiet, graceful death reserved for stars like our Sun. High-mass stars, those born with 8 times the mass of our Sun, or more, live very different lives. They live fast, burn bright, and die young. Because they are so massive, their core gravity is immense. This cranks up the pressure and temperature, causing them to burn through their hydrogen fuel at a furious rate. While our Sun will live for 10 billion years, a massive star might live for only 10 million. When a massive star runs out of hydrogen, it doesn't even pause. Its core collapses and immediately gets hot enough to burn helium into carbon. When the helium runs out, it collapses again, getting even hotter, and fusing carbon into neon. It continues this way, creating a cosmic onion of layers. A core of silicon surrounded by a shell of oxygen surrounded by neon, then carbon, then helium, and finally an outer envelope of hydrogen. It creates heavier and heavier elements fighting against gravity with increasingly desperate and short-lived fuel sources. The fusion of silicon into iron is the last step. Iron is cosmic ash. It is the one element that when fused does not release energy. Instead, it consumes energy. When the star's core becomes pure iron, the furnace doesn't just flicker, it shuts off instantly. This is the moment of catastrophe. With no energy pushing outward, gravity wins completely and catastrophically. The entire massive core of the star, an object larger than our Sun, collapses in on itself in less than a single second. The core smashes down to become an object only a few miles across, a super dense neutron star, or if the star is massive enough, a black hole. The star's outer layers, which were also collapsing inward, now slam into this new incredibly hard neutron star, or the event horizon of the black hole. The material bounces. This bounce creates a shockwave of unimaginable power. The shockwave rockets back out through the star's outer layers, superheating them and triggering one last massive burst of fusion. The star detonates. This is a supernova. For a few weeks, this single exploding star can outshine its entire home galaxy of billions of stars. It is an explosion of violence so great it is difficult to comprehend. But this violence is not just destructive, it is necessary. That shockwave is the universe's forge. The energy in the explosion is so immense that it is the only place in the universe where elements heavier than iron can be created. Every bit of gold in our jewelry, the silver in our electronics, the uranium used for nuclear power, all of it was created in the flash of a supernova explosion. But more importantly, the explosion scatters all the elements the star created during its life. The carbon, the oxygen, the nitrogen, the silicon, the iron, far and wide across the galaxy. This enriched material, this star stuff, seeds the surrounding clouds of gas. This is the completion of the cycle. The star stuff from the supernova mixes with the pristine hydrogen in a new nebula. This enriched gas cloud then collapses to form the next generation of stars, and crucially, it forms the planets that orbit them. This is where we come from. The planets in our solar system, including Earth, were formed from the debris of long-dead massive stars. The carbon that forms the basis of all known life, the nitrogen in our DNA, the calcium in our bones, the oxygen we breathe, and the iron in our blood that carries that oxygen, every single one of those atoms was cooked in the core of a massive star that lived and died billions of years ago. That star exploded, scattering its gifts across the galaxy, and that material eventually coalesced to form our sun, our planet, and us. We are in the most literal sense made of star stuff. We are the children of the stars. The cosmos is not just something we look at, it is something we are part of. Every atom in our bodies is a tiny piece of a star that died recycled by the galaxy to give rise to new life. And so we drift, floating away from the comforting, familiar lights of our own stellar neighborhood. Let your mind travel outwards past the last glittering stars of our own spiral arms, past the glowing thin halo of our Milky Way, and into the truly deep, dark and silent void. Out here the emptiness is vast, but it is not completely empty. If you are lucky enough to be somewhere truly dark, far from the energetic glare of human cities on a clear and moonless night, you can look up towards the constellation named for the mythical princess Andromeda. You are not looking for a star. A star is a pinprick of light, sharp and bright. You are looking for the opposite. You are looking for a smudge. A faint fuzziness. It is so faint you might miss it if you look directly at it. It's a whisper of light, a tiny, elongated, ghostly cloud. For thousands of years, astronomers who mapped the sky saw this patch. They called it the Andromeda Nebula. A nebula, a cloud of gas existing right here, a neighbour inside our own galaxy, just a little bit of cosmic fog. But that faint patch of light holds a secret, a profound, universe-changing secret. That little cloud is the most distant object your eyes will ever see without help. The light from that smudge, it is old, it is ancient light. It has been travelling for 2.5 million years to reach you. Let that feeling sink in. 2.5 million years. When the photons of light that are now hitting your retina first began their long journey across the dark, our own planet was a different world. Our distant human ancestors were just learning to walk upright on the African savanna. The great ice ages were just beginning to shape the continents we know today. And all that time, through all of human evolution, through all of recorded history, this light has been speeding silently across the immense dark gap between something and us. That faint smudge is not a cloud. It is our neighbour, the great Andromeda galaxy. Realising this changed everything. For the longest time we lived in a cosy, comfortable universe. We believed that our Milky Way was the universe. Everything we saw in the sky, every star, every nebula was part of our home. It was a vast but single island of light in an infinite empty ocean. But this one fuzzy patch, Andromeda, caused a problem. In the 1920s, the scientific community was divided. They called it the Great Debate. Were these spiral nebulae just clouds of gas spinning within our own Milky Way, or were they something else? Were they, as some dared to suggest, island universes in their own right? The idea was staggering. that the universe wasn't just our galaxy, but perhaps billions of other galaxies. An astronomer named Edwin Hubble, using the new and powerful Hooker telescope on Mount Wilson in California, dedicated himself to solving this mystery. He aimed the telescope at Andromeda night after night. He was not just looking at it, he was looking for a special kind of star. A variable star, one that rhythmically brightens and dims like a beating heart. These stars are like cosmic lighthouses. If you can measure how fast one pulses, you can calculate its true actual brightness. And if you know its true brightness, you can compare it to how dim it appears from Earth. And from that you can calculate its exact distance. Hubble found one and then another. He did the math. And the answer he found did not just solve the debate, it shattered our entire model of reality. The numbers showed that this nebula was not a few thousand light years away, it was nearly 1 million light years away, his first estimate, which we now know is even further at 2.5 million. It was impossibly far, it was completely, undeniably outside our own galaxy. It was not a cloud of gas. It was a city of stars, a galaxy just like our own. In that moment, the universe we thought we knew vanished. It was replaced by a cosmos so large, so full of other islands that the human mind can barely hold the scale of it. We were not the universe. We were just one island. In an ocean of islands, and Andromeda was the first other shore we ever identified. So what is this great neighbour like? When we turn our modern telescopes, like the Hubble Space Telescope that bears Edwin's name, towards Andromeda, we see a stunning reflection of ourselves. It is a spiral galaxy just like us. We see those beautiful, sweeping arms curling outwards traced by dark lanes of interstellar dust. We see the brilliant blue-white glitter of young hot regions where new stars are being born. We see a bright yellowish-white core, a dense central bulge where billions of older stars orbit together in a golden haze. It is tilted on an angle from our perspective, so we see it as a great elongated oval of light. It's like looking at a dinner plate from the side, not from directly above. It is our twin, but it is not our identical twin, it is our bigger sister. Our Milky Way is immense. We think it has somewhere between 200 and 400 billion stars. A truly vast number, but Andromeda is the heavyweight champion of our local group of galaxies. It stretches over 220,000 light-years from tip to tip, far larger than our own 100,000 light-year span, and its stellar population, it is staggering. Astronomers estimate that Andromeda is home to 1 trillion stars, 1,000 billion stars. Think of every star in our galaxy, every single one. Now imagine doubling that or even tripling it and packing it into a slightly larger space. It is a magnificent, sprawling metropolis of light turning with slow, majestic grace in the darkness. It is our cosmic mirror showing us what a grand spiral galaxy looks like from the outside, and this beautiful massive mirror is falling right towards us. This is perhaps the most fascinating part of our relationship with Andromeda. We are bound together by a gravity. While most of the universe is expanding with galaxies rushing away from each other, we are not. We are in what's called the local group, and in this local neighbourhood, gravity still wins. Andromeda and the Milky Way are the two largest members of this group, and they are pulling on each other an insistent, steady gravitational tug that has been reeled them in for billions of years. We are moving towards each other at a speed of about 110 kilometers per second. That's over 400,000 kilometers per hour. It sounds incredibly fast, but in space the distances are so great that this is a slow drift. The word for this event is collision. The Andromeda-Milky Way collision, and that word collision brings to mind images of violence, of fire, of destruction, 2 trucks hitting head-on. You must let go of that image. That is not what will happen. The universe is defined by its emptiness. A galaxy is not a solid object, it is a collection of stars, gas and dust that are separated by an almost perfect vacuum. The distance between the stars is the important part. Our nearest stellar neighbour, Proxima Centauri, is over 4 light-years away. That is the typical spacing. So when this collision happens, it is not a crash, it is a merger, it is a dance. The 2 galaxies will not slam into each other, they will pass through each other. Like 2 ghosts or 2 clouds of smoke, they will interpenetrate. The stars themselves, they will not hit. The chance of our Sun colliding with a star from Andromeda is practically zero. The space is too big. Everyone will just displaced each other. So no, it is not an explosion, but it will be chaotic. Gravity will be the choreographer. As these 2 massive systems, one with 1 trillion stars, one with 400 billion, weave through one another, their mutual gravity will wreak havoc on their beautiful, delicate spiral shapes. They will be torn apart. Imagine long streams of stars like cosmic ribbons being pulled out of the galaxies and flung hundreds of thousands of light years into the empty void. Our own solar system will almost certainly be thrown onto a new, completely different orbit. Perhaps we will be tossed far out into the new expanded halo to live in a dark, lonely part of the new galaxy. Or perhaps we will be dragged deep into the new hyperdense, chaotic core. We cannot know our Proxima's fate, but we know the view. Oh, the view would be unimaginable. Imagine a night sky not with one faint familiar band of the Milky Way, but a sky filled, torn and ablaze with the arms of Andromeda stretched and warped, a trillion new stars dominating the view from horizon to horizon. It would be the greatest light show in the history of our planet. This gravitational dance will not be a single event. After, so they pass through each other the first time their momentum will carry them apart, but gravity will pull them back. They will slow down, stop and then fall back together. Again, they will pass through each other several times over hundreds of millions of years. With each pass they will blur, their elegant spiral arms will be scrambled, the chaos will stir up all the gas and dust, triggering a massive galaxy-wide burst of new star formation. A final brilliant flash of blue-white brilliance. But eventually after this long waltz they will settle. They will merge, they will become one. The Milky Way and Andromeda will be gone. In their place will be a new single super galaxy. Astronomers with a bit of humour call this future galaxy Milkomeda, and it will likely not be a spiral. The chaotic merger will have randomized the orbits of all the stars. It will be what we call a giant elliptical galaxy, a massive, quiet, roundish blob of golden aging stars. This is our future, our destiny. And when does this all begin? When does the dance start? In about 4.5 billion years, 4.5 billion years. It is a span of time that is itself cosmic. Our sun is about 4.5 billion years old. So this grand merger is one full lifetime of our star away. By then our sun will be an aging star. It will be growing hotter, brighter, expanding into a red giant Earth. Our home will likely no longer be a habitable blue-green world. So we as humans will not be here to see it. But the universe does not care about our timelines. We are living in a very specific calm moment. We are living in the present of the universe. But the universe's present is incredibly slow. Right now, as you lie here, Andromeda is getting closer. Every second is 110 kilometers closer. We are watching in the slowest motion imaginable two titans of the cosmos falling into a gravitational embrace that will one day reshape our entire corner of the universe. It is not something to fear. It is something to behold. It is the gentle, powerful and inevitable rhythm of the cosmos. A rhythm that plays out over billions and billions of years. And now as we contemplate this slow grand future, let's drift even further. Past Andromeda, past our local group, and out into the true ocean of galaxies. Our Milky Way is not alone. It's part of a large gravitationally bound family known as the local group. Think of it as our cosmic neighborhood. A collection of galaxies all moving together through the vast emptiness of intergalactic space. When we picture our group, we often think of the big two, our own Milky Way and the Andromeda galaxy. Andromeda is our closest large neighbor, a truly massive spiral galaxy about 2.5 million light-years away. It's so large and close that you can even see it with the naked eye from a dark sky location, appearing as a faint fuzzy smudge. But the local group isn't just these two giants. That would be like describing a major metropolitan area by only mentioning its two biggest cities. The group is actually composed of more than 50 galaxies, and the vast majority of these are small dwarf galaxies. These are like the small towns, villages and suburbs that orbit the two major urban centres. The third largest member, the Triangulum Galaxy, is also a spiral but significantly smaller than either the Milky Way or Andromeda. The rest are tiny, faint and often clustered around the larger members held in their gravitational grip. Among the most famous of these companion galaxies are the Magellanic Clouds. Named after the explorer Ferdinand Magellan, whose crew was the first to report them to Europeans, these two galaxies are only visible from the southern hemisphere. They look like detached, glowing patches of the Milky Way, and for centuries their true nature was a mystery. We now know they are small irregular galaxies that are in a very close and chaotic dance with our own. The large Magellanic Cloud and the small Magellanic Cloud are relative neighbours, only about 160,000 and 200,000 light-years away respectively. Unlike the neat spiral of our galaxy, they are messy and disorganised. This is partly because the Milky Way's immense gravity is tearing them apart. As they orbit us, our gravity pulls long invisible streamers of hydrogen gas from them, creating a structure called the Magellanic Stream that wraps partway around our galaxy. They are not peaceful neighbours. They are in the process of being slowly consumed. This variety of shapes our neat spiral, the messy Magellanic Clouds, begs a bigger question. What do all the other galaxies in the universe look like? When we point our telescopes beyond the local group, we see not thousands but trillions of other galaxies. It's a cosmic zoo filled with an astonishing variety of forms. In the 1920s, the astronomer Edwin Hubble was the first person to try and organise this zoo. He created a classification system often called the Hubble tuning fork diagram that sorted galaxies by their appearance. This system is still the foundation of how we talk about galaxies today. First, there are the spirals like our Milky Way and Andromeda. These are perhaps the most beautiful. They are flat, spinning disks of stars, gas and dust. The centre of the disk has a bright round bulge, which is mostly made of older, dimmer stars. The disk itself is where the action is. It's crisscrossed by magnificent spiral arms, which are bright bluish and full of glowing nebulae. These arms are not solid structures. They are density waves, like a traffic jam moving through the disk's material. As gas and dust clouds pass through this jam, they get compressed, triggering a massive wave of new star formation. This is why the arms are so bright and blue. They are filled with huge, hot, brilliant blue stars. These stars live very fast and die young, exploding as supernovae. A spiral galaxy is a living, active, dynamic place. Then you have the elliptical galaxies. If spirals are vibrant, star-forming cities, ellipticals are the universe's ancient, quiet retirement communities. They are completely different. They are not flat disks. Instead, they are massive, three-dimensional, fuzzy-looking ovals like a cosmic football or a giant swarm of bees. Their most defining feature is their colour, a dim reddish yellow. This colour tells us everything we need to know. They are composed almost entirely of old red stars. They have no gas, no dust, and no blue stars. This means their days of star formation are long over. They are often called red and dead. While this sounds dull, ellipticals are often the most massive galaxies in the universe, true cosmic behemoths that sit at the centre of vast galaxy clusters, having grown to their enormous size over billions of years. Finally, there are the irregular galaxies. These are the misfits. They have no defined shape. They lack the majestic arms of a spiral or the smooth symmetrical glow of an elliptical. They are simply chaotic, messy collections of stars and gas. The Magellanic Clouds are a perfect example. Their chaotic shape is often a sign of a troubled past or present. Many irregulars are the result of gravitational interactions or collisions with other galaxies. This leads to the biggest secret of the galactic zoo: the shapes are not fixed. Galaxies are not isolated islands. They are dynamic objects that interact, collide, and merge. The engine of galactic evolution is galactic cannibalism. Gravity pulls everything together. Over the vast spans of cosmic time, galaxies will pull on each other. When a large galaxy like the Milky Way has a smaller galaxy nearby, like a dwarf galaxy, its gravity is stronger. It will pull the smaller galaxy in, stretching it out and ripping it apart. The stars from the smaller galaxy are not destroyed, but they are pulled into long tidal streams that wrap around the larger galaxy, eventually mixing in and becoming part of the new larger system. This is not a theoretical idea, it is happening right now. Our own Milky Way is currently in the process of eating several smaller dwarf galaxies. The most famous of these is the Sagittarius dwarf spheroidal galaxy. It's on the opposite side of the galaxy from us, and our Milky Way's gravity has torn it to shreds. Its stars now form a gigantic stream that wraps around our galaxy's poles. Our galaxy is a cannibal, and it has grown to its current size by consuming hundreds of smaller galaxies over its 13 billion year life. This process of creative destruction is how the different shapes are formed. What happens when two large spiral galaxies like the Milky Way and Andromeda collide? For decades, this was just a simulation, but we now see it happening all over the universe. The collision triggers a starburst, a galaxy-wide frenzy of star formation so intense it uses up all the available gas in a few 100 million years. The two spiral disks are completely destroyed at their stars thrown into new random three-dimensional orbits. With all the gas gone and the stars settled into a new chaotic swarm, what's left a giant red and dead elliptical galaxy. The elegant spirals we see today are the ones that have lived relatively quiet lives. The giant messy ellipticals are the ancient survivors of a violent chaotic past built from the wreckage of countless smaller galaxies. The universe is not a static display. It is a place of constant slow-motion change, where destruction and creation are two sides of the same cosmic coin. In our journey so far, we have been pulling back our view step by step. We looked at our solar system, a tiny cozy nest. We pulled back to see our star, the Sun, among its neighbours. Then we saw our galaxy, the Milky Way, a vast spinning island of light. We saw it as just one of many in our local group, and that group in turn as a small part of the massive Virgo supercluster. At every stage the scale has become almost too large to hold in our minds. Now we must take the final step back. Let your mind zoom out faster and faster. The Virgo supercluster with its thousands of galaxies shrinks until it is just a bright smear. We pull back further, and that smear becomes a single point of light indistinguishable from the cluster next to it. We keep going, past millions of galaxies, past billions of them. We are now looking at the universe on the largest possible scale. We are looking at the entire observable cosmos, a map stretching across 93 billion light-years. And when we look at this map, what do we see? We have journeyed across the cosmic web, a staggering network of light and gravity connecting billions of galaxies each, a city of billions of stars. We have seen how these galaxies spin, merge and cluster, driven by the invisible hand of dark matter. But this grand tour, this entire cosmic structure, forces us to ask the ultimate question of why. Where did this network come from? Where did the galaxies, the stars, the matter, and the very space they occupy originate? To answer this, we must rewind our clock not by millions or even billions, but by 13.8 billion years. We must go back to the very first moment, to the origin of time itself. The story of our universe begins with what is popularly and somewhat misleadingly called the Big Bang. This name conjures an image of a colossal explosion, like a bomb detonating at a single point in the centre of a dark, empty void. This picture is wrong. The Big Bang was not an explosion in space. It was the beginning of space. It was the beginning of time. It was the beginning of everything. The simplest way to understand this is to imagine a balloon. Imagine you draw tiny dots on the surface of this deflated balloon. These dots represent the first clusters of energy which will later become galaxies. Now you start to inflate the balloon. What happens? The dots move away from each other, but they are not flying across the balloon surface. The surface itself, the very fabric of space in this analogy, is stretching. Every dot moves away from every other dot. From the perspective of any single dot, it looks like all the other dots are rushing away from it. This is exactly what we observe in our universe. When we look at distant galaxies, they are all moving away from us, and the farther away they are, the faster they appear to be moving. This is not because we are at the centre of a great explosion. It is because the fabric of space-time itself has been expanding ever since the first moment. In its first tiny fraction of a second, the universe was not a place. It was a condition. It was a singularity, a point of almost infinite density and unimaginable temperature, hotter than anything we can truly comprehend. All the energy, all the matter, and all the space of the entire observable universe was compressed into a region smaller than an atom. In this instant, the laws of physics as we know them did not apply. But as this point began its rapid expansion, the universe was born. Time began to tick. The forces of nature, gravity, electromagnetism, and the nuclear forces separated from a single unified state. The universe entered its infancy, a period we call the first 3 minutes. This was not a time of stars and planets. It was a chaotic, brilliant, and blindingly hot place. Imagine a soup, not of food, but of pure high-intensity energy, and the most basic fundamental particles. For these first moments, the universe was so hot and so dense that even the building blocks of atoms, protons, and neutrons could not hold themselves together. It was a churning sea of their own tiny components, particles we call quarks and gluons, swimming in an ocean of high-energy light photons and other exotic particles. As the universe continued to expand, it also began to cool. Just like the air from a compressed can feels cold as it expands, the expanding universe cooled its energy. After just 1 second, it was cool enough down to a mere few trillion degrees for protons and neutrons to form. The universe was now a soup of particles, protons, which would become the heart of hydrogen, neutrons, and electrons, all zipping around in a bath of intense radiation. This is also where a great mystery was settled. Energy can become matter, a truth revealed by Albert Einstein's famous equation, energy equals mass times the speed of light squared. When energy created matter, it always created a matching particle of antimatter. When matter and antimatter meet, they annihilate each other, turning back into pure energy. For some reason, in that first chaotic second, a tiny bit more matter was created than antimatter. For every billion antimatter particles, there was 1 billion and 1 matter particles. That tiny leftover fraction that 1 in a billion cosmic imbalance is everything you see. It is the solid ground beneath your feet, the air you breathe, and the stars in the sky. The rest annihilated itself, filling the young universe with even more light. By the time the universe was 3 minutes old, it had cooled enough for protons and neutrons to stick together. Nuclear fusion, the same process that powers our sun, began. Protons and neutrons fused to form the first simple atomic nuclei, mostly hydrogen, 1 proton, and a significant amount of helium, 2 protons, 2 neutrons with tiny traces of lithium. And then this first flurry of creation stopped. The universe had become too large and too cool for fusion to continue. The recipe for the universe was set. It was about 75% hydrogen, 25% helium, and a fog of free-roaming electrons and photons light. This fog was so thick that the universe was opaque. Light could not travel more than a few inches before being bounced off a free electron like a car's headlights in a dense fog. This cosmic fog would persist for a very long time. For the next 380,000 years, the universe expanded and cooled in a state of murky brightness. The hydrogen and helium nuclei wanted to capture the free electrons to become stable neutral atoms. But the universe was still too hot. The photons of light were so energetic that they would immediately knock any captured electron free, keeping the fog in place. Then the universe crossed a critical threshold. The temperature dropped to about 3,000 degrees, roughly the surface of a red star. At this point, the photons of light no longer had enough energy to keep the electrons free. The hydrogen and helium nuclei finally captured the electrons, forming the first stable neutral atoms. This event, called recombination, changed everything. With the electrons now locked into atoms, the fog cleared. Instantly, all the light that had been trapped bouncing around like a pinball for 380,000 years was suddenly set free. It flooded the universe and streamed outwards in all directions, free to travel unobstructed forever. This is the first light. It is the oldest light in the universe. And it is still here. We can still see it. This afterglow of creation is called the cosmic microwave background, or CMB. As the universe has expanded for the 13.8 billion years, since that moment the waves of this ancient light have been stretched just like the balloon's surface. This stretching shifted the light from visible light into the low-energy microwave part of the spectrum. When you see a map of the CMB, you are looking at a baby picture of the universe. It is a snapshot of the cosmos when it was just 380,000 years old. It is an echo of the beginning, and it is everywhere. No matter where you point a radio telescope in the sky, in the empty spaces between stars and galaxies, you will find this faint, ancient warmth. It is the hiss of the universe itself. This map is perhaps the most important discovery in all of science. It is not perfectly uniform. There are tiny, almost invisible splotches areas that are a fraction of a degree hotter or colder than others. These tiny variations were the seeds of all structure. The slightly denser, colder spots were where gravity would begin its slow, patient work. With the first light now streaming freely, a new era began, the Dark Ages. The universe was now transparent, but it was also dark. The hot fog had cleared, but there were no new sources of light. There were no stars, no galaxies, no cities, no lights. The universe was a vast, silent, expanding ocean of darkness. This darkness was filled with the ingredients created in the first 3 minutes, enormous diffuse clouds of hydrogen and helium gas. For hundreds of millions of years, this was the state of the cosmos. The only thing happening was gravity. In the vast silence, gravity began to pull on those tiny, denser regions seen in the CMB map. Ever so slowly, atoms of hydrogen were drawn together. What began as a slightly denser wisp of gas became a small cloud. As the cloud grew, its own gravity increased, pulling in more gas from its surroundings. Over millions of years, these clouds became denser and denser. The Dark Ages were the universe's quiet waiting room. Gravity was building the stage for the next great act. After perhaps 100 to 200 million years of darkness, something incredible happened. In the hearts of the most massive, densest clouds of hydrogen gas, the pressure and temperature became so extreme that a new fire was lit. The hydrogen atoms at the core of these clouds were crushed together so intensely that they fused, becoming helium. This was the birth of the first stars. This was the cosmic dawn. The first lights to pierce the darkness of the universe were switched on ending the Dark Ages. These first stars, which scientists call population 3 stars, were nothing like our Sun. They were monsters. Because they were formed only from the pure hydrogen and helium of the Big Bang, they were able to grow to enormous sizes. The first stars were perhaps 100 or even 300 times more massive than our own Sun. Because they were so massive, they were unimaginably hot and bright. They did not shine with the friendly yellow-white light of our sun. They blazed with an intense blue-white light pouring staggering amounts of ultraviolet radiation into the surrounding darkness. They were the beacons that lit up the universe. But the more massive a star, the faster it burns. Their lives were brilliant but incredibly short. While our sun will live for 10 billion years, these first giants lived for only a few million years, and then they died. And their deaths were the most important event since the Big Bang itself. They exploded in the most powerful supernovae the universe has ever known. In these final catastrophic explosions, the star's cores were crushed, triggering a runaway fusion process. For the first time, new heavier elements were forged. The Big Bang created only hydrogen and helium. Inside the furnaces of these first stars, and especially in their explosive deaths, carbon, oxygen, silicon iron, and all the other heavy elements were created and blasted out into space. These explosions sent out shockwaves that seeded the nearby clouds of hydrogen with these new heavier materials. This stardust changed the recipe of the universe. The next generation of stars would form from these polluted clouds. They would be smaller, longer-lived, and crucially, they would be able to form rocky planets. This was the start of the cycle of matter. These first stars were the great ancestors. They lived fast and died hard, but in their deaths they provided the raw materials, the carbon for life, the oxygen for water, the silicon for rocks, and the iron for our blood, that would eventually lead to the formation of galaxies, planets, and us. The echo of the Big Bang had given way to the first light of the first stars, and the universe would never be dark again. Is it chaos? Is it like sand thrown onto a dark floor, scattered randomly? No, it's perhaps the most profound and beautiful discovery of modern science. The universe has a structure. It is not random at all. When we map the locations of millions and millions of galaxies, we find they form a breathtaking, intricate pattern. A vast interconnected network, we call it very simply the cosmic web. Imagine for a moment a spider's web on a cold morning covered in dew. You see the long, delicate threads shining with light. You see how they connect to each other, forming joints and knots. And you see the large empty spaces between the threads. The universe is built just like this. The threads of this web are called filaments. These are unimaginably long, twisting rivers of matter stretching for hundreds of millions of light years. And along these filaments, galaxies are strung together like pearls on a necklace. These filaments are the highways of the cosmos. This is where the stuff is. This is where the galaxies live and flow and interact. Where these filaments meet, where they cross and tangle, they form dense, bright knots. These are the superclusters, like the Virgo supercluster we saw earlier. They are the great busy cities of the universe, blazing with the light of thousands of galaxies brought together. But perhaps the most striking, the most humbling part of the cosmic web is not the threads. It is the empty space between them. These spaces are called the voids. These are not just empty. They are profoundly, fundamentally empty. They are vast, dark oceans of almost perfect nothing. A single void can be hundreds of millions of light years across. If our Milky Way galaxy were inside one of these voids, our night sky would be almost completely dark. We would look out and see nothing. Maybe one or two faint, lonely galaxies on the distant horizon. The voids are the great silences of the cosmos, and they make up most of the universe. The structure of the universe is not a collection of things, it is a tapestry of nothing and something. There are a few ways to picture this in your mind to make it feel more familiar. Think of a sink filled with soap bubbles, a thick foam. The galaxies, the filaments, the clusters, they all exist on the thin, wet walls of the bubbles. They trace the surface where one bubble touches another. But the inside of every bubble, that is the void. That is the empty air. The universe at its largest scale is a foam of bubbles. Or if you prefer, think of a neural network. Think of the human brain. Billions of tiny cells, the neurons. Each one is a small point, but they are not isolated. They are reaching out, sending tiny fibers, connecting to one another, forming a structure of thought, a web of consciousness. The universe is like this. Billions of galaxies, each one a point of light reaching out across the darkness, connected by the invisible threads of gravity, forming the grand structure of reality itself. So the next question is, where are we in this grand picture? Where is our home? Where is the Milky Way? We are not in one of the great lonely voids. We are fortunate. We live in a relatively busy, vibrant neighborhood. We are located on one of the bright threads. Our home supercluster, the one we are a part of, has a beautiful name. It is called Laniakea. This is a Hawaiian name. It was given to this structure by the astronomers who first mapped it. Laniakea means immense heaven, and it is truly immense. Laniakea is our home filament. It contains our own Virgo supercluster and many others. It is home to roughly 100,000 galaxies, including our Milky Way. This single thread in the cosmic web stretches for more than 500 million light-years. And it is not just sitting still. This entire structure, this immense heaven, is moving. It is flowing. All 100,000 galaxies in Laniakea are being pulled like a great river in space toward a single massive point. We cannot see this point clearly. It is hidden behind the dust of our own galaxy, but we call it the Great Attractor. We are a tiny speck of dust on a single planet orbiting a single star in a single galaxy, which is just one of 100,000, all flowing together in a single thread of light. We are one drop of water in the river of Laniakea. This leads us to the final and perhaps the greatest mystery of all. Why? Why this shape? Why the web? Why the filaments? And why the voids? If you just threw a handful of sand, it would scatter. It would not form an intricate web. If the universe was only made of the stars and the gas and the dust that we can see, its own gravity would not be strong enough to create this. This beautiful structure would not exist. Something else must be there. Something must be holding it all together. Something must have built this structure. This something is the great ghost of the cosmos. We call it dark matter. We call it dark because we cannot see it. It does not shine. It does not burn. It does not reflect light. It does not interact with us or with any of our equipment. It is completely, totally invisible. So how do we know it is there? We know it is there the same way you know the wind is there on a dark, moonless night. You cannot see the wind, but you can see what it does. You see the leaves on the trees shake. You see the branches bend and sway. You hear it whisper through the grass. You see its effect on the world you can see. We see the effects of dark matter everywhere we look. We see galaxies spinning so fast that if they were only made of the stars, we see they should fly apart into space. But they do not. An invisible halo of dark matter with its powerful gravity holds them together. We see light from distant ancient objects bending and warping as it passes through empty space. It bends because the gravity of the dark matter filling that empty space is acting like a lens changing the path of the light. And most of all, we see this, the cosmic web. This web is the greatest proof of all. In the very beginning of the universe, long before the first stars were born, this invisible dark matter began to gather. It was the only thing that had enough gravity to pull itself together. It clumped and it collected, forming an invisible skeleton for the cosmos. It formed the first invisible filaments and the first invisible voids. Then all the normal matter, the hydrogen and helium gas that would one day become you and me, and the stars began to feel the pull of this invisible scaffolding. The gas was pulled by gravity into the shapes the dark matter had already made. It was like water flowing into the dry bed of a river. The gas flowed along the invisible filaments, collecting in the invisible knots. The cosmic web that we see today, the bright strings of shining galaxies, this is just the visible paint on top of a much larger invisible sculpture. The galaxies are like bright white foam riding on the waves of a deep, dark, unseen ocean. This invisible ocean, this dark matter, makes up about 85% of all the matter in the universe. Think about that. Everything we have ever seen. Every star, every planet, every nebula, every person, all of it is only about 15% of the universe. We are the exception. We are the foam. The vast majority of the cosmos is this silent, unseen, gentle presence that holds the universe together. So as you rest, as you drift, let your mind visualize this grand cosmic structure. Feel yourself as a part of it. A single point of light on a single glowing thread. A thread that is part of a web that stretches from one end of time to the other. You are not isolated. You are not alone. You are connected. Connected by gravity. Connected by light to every other star in every other galaxy on every other thread. You are a part of the immense heaven, a part of the web, and you are held gently in the invisible gravitational embrace of the dark matter that forms the quiet, strong, unseen skeleton of everything. Rest now inside this structure. Feel the deep, quiet safety of the web, the dark stillness of the voids and the gentle flowing light of the filaments. We have journeyed across the cosmic web, a staggering network of light and gravity connecting billions of galaxies each, a city of billions of stars. We have seen how these galaxies spin, merge and cluster driven by the invisible hand of dark matter. But this grand tour, this entire cosmic structure forces us to ask the ultimate question of why? Where did this network come from? Where did the galaxies, the stars, the matter, and the very space they occupy originate? To answer this, we must rewind our clock not by millions or even billions, but by 13 billion years. We must go back to the very first moment, to the origin of time itself. The story of our universe begins with what is popularly and somewhat misleadingly called the Big Bang. This name conjures an image of a colossal explosion, like a bomb detonating at a single point in the center of a dark, empty void. This picture is wrong. The Big Bang was not an explosion in space, it was the beginning of space, it was the beginning of time, it was the beginning of everything. The simplest way to understand this is to imagine a balloon. Imagine you draw tiny dots on the surface of this deflated balloon. These dots represent the first clusters of energy which will later become galaxies. Now you start to inflate the balloon. What happens? The dots move away from each other, but they are not flying across the balloon surface. The surface itself, the very fabric of space in this analogy, is stretching. Every dot moves away from every other dot. From the perspective of any single dot, it looks like all the other dots are rushing away from it. This is exactly what we observe in our universe. When we look at distant galaxies, they are all moving away from us, and the farther away they are, the faster they appear to be moving. This is not because we are at the center of a great explosion, it is because the fabric of space-time itself has been expanding ever since the first moment. In its first tiny fraction of a second, the universe was not a place. It was a condition. It was a singularity, a point of almost infinite density and unimaginable temperature, hotter than anything we can truly comprehend. All the energy, all the matter, and all the space of the entire observable universe was compressed into a region smaller than an atom. In this instant, the laws of physics as we know them did not apply. But as this point began its rapid expansion, the universe was born. Time began to tick. The forces of nature, gravity, electromagnetism, and the nuclear forces separated from a single unified state. The universe entered its infancy, a period we call the first 3 minutes. This was not a time of stars and planets. It was a chaotic, brilliant, and blindingly hot place. Imagine a soup, not of food, but of pure, high-intensity energy and the most basic fundamental particles. For these first moments, the universe was so hot and so dense that even the building blocks of atoms, protons, and neutrons could not hold themselves together. It was a churning sea of their own tiny components, particles we call quarks and gluons, swimming in an ocean of high-energy light photons and other exotic particles. As the universe continued to expand, it also began to cool. Just like the air from a compressed can feels cold as it expands, the expanding universe cooled its energy. After just 1 second, it was cool enough down to a mere few trillion degrees for protons and neutrons to form. The universe was now a soup of particles, protons, which would become the heart of hydrogen, neutrons, and electrons, all zipping around in a bath of intense radiation. This is also where a great mystery was settled. Energy can become matter, a truth revealed by Albert Einstein's famous equation, energy equals mass times the speed of light squared. When energy created matter, it always created a matching particle of antimatter. When matter and antimatter meet, they annihilate each other, turning back into pure energy. For some reason, in that first chaotic second, a tiny bit more matter was created than antimatter. For every billion matter particles, there was 1,000,000,001 matter particles. That tiny leftover fraction, that 1 in a billion cosmic imbalance, is everything you see. It is the solid ground beneath your feet, the air you breathe, and the stars in the sky. The rest annihilated itself, filling the young universe with even more light. By the time the universe was 3 minutes old, it had cooled enough for protons and neutrons to stick together. Nuclear fusion, the same process that powers our sun, began. Protons and neutrons fused to form the first simple atomic nuclei, mostly hydrogen, 1 proton, and a significant amount of helium. 2 protons, 2 neutrons with tiny traces of lithium. And then this first flurry of creation stopped. The universe had become too large and too cool for fusion to continue. The recipe for the universe was set. It was about 75% hydrogen, 25% helium, and a fog of free-roaming electrons and photons light. This fog was so thick that the universe was opaque. Light could not travel more than a few inches before being bounced off a free electron like a car's headlights in a dense fog. This cosmic fog would persist for a very long time. For the next 380,000 years, the universe expanded and cooled in a state of murky brightness. The hydrogen and helium nuclei wanted to capture the free electrons to become stable neutral atoms, but the universe was still too hot. The photons of light were so energetic that they would immediately knock any captured electron free, keeping the fog in place. Then the universe crossed a critical threshold. The temperature dropped to about 3,000 degrees, roughly the surface of a red star. At this point, the photons of light no longer had enough energy to keep the electrons free. The hydrogen and helium nuclei finally captured the electrons, forming the first stable neutral atoms. This event, called recombination, changed everything. With the electrons now locked into atoms, the fog cleared instantly. All the light that had been trapped bouncing around like a pinball for 380,000 years was suddenly set free. It flooded the universe and streamed outwards in all directions, free to travel unobstructed forever. This is the first light. It is the oldest light in the universe, and it is still here. We can still see it. This afterglow of creation is called the cosmic microwave background, or CMB. As the universe has expanded for the 13.8 billion years, since that moment the waves of this ancient light have been stretched just like the balloon's surface. This stretching shifted the light from visible light into the low-energy microwave part of the spectrum. When you see a map of the CMB, you are looking at a baby picture of the universe. It is a snapshot of the cosmos when it was just 380,000 years old. It is an echo of the beginning, and it is everywhere. No matter where you point a radio telescope in the sky, in the empty spaces between stars and galaxies, you will find this faint, ancient warmth. It is the hiss of the universe itself. This map is perhaps the most important discovery in all of science. It is not perfectly uniform. There are tiny, almost invisible splotches areas that are a fraction of a degree hotter or colder than others. These tiny variations were the seeds of all structure. The slightly denser, colder spots were where gravity would begin its slow, patient work. With the first light now streaming freely, a new era began, the Dark Ages. The universe was now transparent, but it was also dark. The hot fog had cleared, but there were no new sources of light. There were no stars, no galaxies, no cities, no lights. The universe was a vast, silent, expanding ocean of darkness. This darkness was filled with the ingredients created in the first 3 minutes, enormous diffuse clouds of hydrogen and helium gas. For hundreds of millions of years, this was the state of the cosmos. The only thing happening was gravity. In the vast silence, gravity began to pull on those tiny, denser regions seen in the CMB map. Ever so slowly, atoms of hydrogen were drawn together. What began as a slightly denser wisp of gas became a small cloud. As the cloud grew, its own gravity increased, pulling in more gas from its surroundings. Over millions of years, these clouds became denser and denser. The Dark Ages were the universe's quiet waiting room. Gravity was building the stage for the next great act. After perhaps 100 to 200 million years of darkness, something incredible happened. In the hearts of the most massive, densest clouds of hydrogen gas, the pressure and temperature became so extreme that a new fire was lit. The hydrogen atoms at the core of these clouds were crushed together so intensely that they fused, becoming helium. This was the birth of the first stars. This was the cosmic dawn. The first lights to pierce the darkness of the universe were switched on, ending the Dark Ages. These first stars, which scientists call population 3 stars, were nothing like our Sun. They were monsters. Because they were formed only from the pure hydrogen and helium of the Big Bang, they were able to grow to enormous sizes. The first stars were perhaps 100 or even 300 times more massive than our own Sun. Because they were so massive, they were unimaginably hot and bright. They did not shine with the friendly yellow-white light of our Sun. They blazed with an intense blue-white light, pouring staggering amounts of ultraviolet radiation into the surrounding darkness. They were the beacons that lit up the universe. But the more massive a star, the faster it burns. Their lives were brilliant but incredibly short. While our Sun will live for 10 billion years, these first giants lived for only a few million years. And then they died, and their deaths were the most important event since the Big Bang itself. They exploded in the most powerful supernovae the universe has ever known. In these final catastrophic explosions, the star's cores were crushed, triggering a runaway fusion process. For the first time, new heavier elements were forged. The Big Bang created only hydrogen and helium. Inside the furnaces of these first stars, and especially in their explosive deaths, carbon, oxygen, silicon, iron, and all the other heavy elements were created and blasted out into space. These explosions sent out shockwaves that seeded the nearby clouds of hydrogen with these new heavier materials. This stardust changed the recipe of the universe. The next generation of stars would form from these polluted clouds. They would be smaller, longer-lived, and crucially, they would be able to form rocky planets. This was the start of the cycle of matter. These first stars were the great ancestors. They lived fast and died hard, but in their deaths they provided the raw materials, the carbon for life, the oxygen for water, the silicon for rocks, and the iron for our blood that would eventually lead to the formation of galaxies, planets, and us. The echo of the Big Bang had given way to the first light of the first stars, and the universe would never be dark again. Let us drift outwards again beyond the spiral arms of our Milky Way, beyond the local group of galaxies, and into the truly deep dark void. For the longest time we looked at this void and imagined it was static, a fixed, unchanging stage upon which the cosmic play unfolded. We saw the galaxies as great island universes suspended in the dark, beautiful, and eternal. But in the 1920s, an astronomer named Edwin Hubble, using the most powerful telescopes of his day, discovered something that would forever shatter that peaceful illusion. He was observing these distant islands, these galaxies, and he was measuring the light they sent us. He found something strange. Their light was stretched as if it was tired from its long journey. This redshift, as it's called, told him something profound. As they were moving, and not just moving, but moving away from us. It was not a random scatter. Almost every galaxy he could see was racing away from our own. And he found a clear, simple pattern. The farther away a galaxy was, the faster it was moving away. This observation, which became known as Hubble's law, could mean only one thing. The universe itself, the very fabric of space and time, is expanding. It's helpful to think of it like a loaf of raisin bread rising in an oven. Imagine we are on one raisin. As the dough expands, every other raisin moves away from us. A raisin twice as far away will move away twice as fast because there is twice as much dough expanding between us. The raisins themselves aren't moving through the dough itself is carrying them apart. Our universe is the dough, the galaxies are the raisins, and the expansion is real. This discovery was the first solid proof of the Big Bang. If everything is moving apart now, it means that in the past it must have been much, much closer together. But this discovery immediately posed a new question. What is the fate of this expansion? For decades, astronomers believed the answer was simple. The universe is full of stuff. It is full of matter. It is full of galaxies, stars, gas dust, and all of that invisible dark matter that holds it all together. All of this stuff has gravity, and gravity, as we know, pulls, is the great force of cosmic connection. So the logical assumption was that this expansion must be slowing down. The combined gravity of everything in the cosmos should be acting like a giant cosmic brake. It should be pulling back on the expansion, trying to rein it in. Think of throwing a ball up into the air. Gravity is pulling on it, slowing it down. Scientists just wanted to know how much it was slowing down. Would gravity be strong enough to one day stop the expansion completely and pull everything back together in a big crunch? Or would the expansion just slow down forever, the universe coasting into an ever larger but ever slowing future? That was the puzzle. And then came the late 1990s, a moment that changed everything. Two independent teams of astronomers set out to measure this slowdown. They used a specific kind of exploding star, a Type 1 supernova, as a standard candle. These explosions are so bright and so uniform you can use them to measure vast distances across the cosmos. They were looking deep into the past, measuring the expansion rate billions of years ago to compare it to today. They gathered their data, they checked their calculations, they checked them again and again, because the answer they found was impossible. It made no sense. The universe was not slowing down. It was speeding up. Imagine throwing that ball into the air and instead of slowing down, you watch it suddenly accelerate faster and faster, blasting away into the sky as if attached to a rocket. That is the shock they felt. The expansion of the universe is not slowing, it is out of control. This was a complete revolution. Something was wrong, or rather, something new and terrifyingly powerful was at play. What could possibly be strong enough to overcome the collective gravity of all the matter in the universe? What could be pushing the cosmos apart? They gave this mysterious force a name that hides our complete lack of understanding. They called it dark energy. This is not dark matter. Remember, dark matter is the invisible stuff that provides extra gravity pulling things together. We see its effects holding galaxies and galaxy clusters in one piece. Dark energy is the opposite. It is a repulsive force, a sort of anti-gravity. It is a ghost in the machine, a phantom pressure that seems to be a property of empty space itself. As space expands, more space is created, and this new space comes with its own dark energy, which in turn pushes space to expand even faster. And here is the most humbling fact of all. When scientists added up all the matter, we can see the stars, the planets, the gas. It amounts to less than 5% of the universe. When they add in the invisible dark matter, It all totals at most about 30%. The rest of it, the vast overwhelming majority, roughly 70% of everything that exists, is this mysterious invisible unknown push. The dominant force in our cosmos is something we cannot see, cannot detect, and cannot explain. This discovery that the universe is accelerating, driven by a force we do not understand, changed our picture of the future. The simple question of slowing down or reversing was gone. Now we are faced with new and much stranger possibilities. We are now in the realm of gentle speculation. Based on what we see, the destiny of the cosmos seems to be heading in one of two directions. The first, and what many consider the most likely scenario, is known as the Big Freeze, or more poetically, the heat death of the universe. In this future, the dark energy continues to push, remaining at its current constant strength. It doesn't get stronger, it just continues, relentlessly. The effect of this over trillions of years is profound. First, the expansion will carry all other galaxy clusters away from our own. They will be pushed so fast that their light will be stretched into invisibility. One by one, the other galaxies will vanish from our sky. Imagine a night sky billions of years from now that is utterly empty, save for the stars of our own local group, which will have by then merged into one giant galaxy. But the story doesn't end there. Inside this one isolated galaxy, the stars themselves cannot last forever. The process of star formation will eventually stop as all the available gas is used up. The existing stars will burn through their fuel. They will die. The universe will become a graveyard of stellar remnants. Cold white dwarfs, lifeless neutron stars, and silent black holes. The universe will become cold and dark. Given an almost unimaginable amount of time, perhaps even protons themselves will decay, and the last remnants of matter will dissolve. And even the black holes themselves will eventually evaporate, given trillions upon trillions of eons, through a process called Hawking radiation. What is left? A universe that is almost infinitely large, almost infinitely cold, and almost perfectly empty. A vast, dark, silent void where nothing happens forever. It is the long, slow, quiet end, the heat death, a final gentle fading to black. But there is another, more violent possibility. This one is called the Big Rip. This ending depends on what dark energy actually is. What if it isn't constant? What if this phantom energy, as it is sometimes called, is actually growing stronger over time? If this is the case, then the acceleration will itself accelerate. The expansion won't just continue, it will become uncontrollable. As this phantom energy grows, it will begin to tear the universe apart piece by piece. First, its repulsive force will become stronger than the gravity that holds galaxy clusters together. The great superclusters will be torn apart. Then, as the energy continues to build, it will overcome the gravity holding individual galaxies together. Our own Milky Way would be unwound, its billions of stars flung out into the expanding empty darkness. But it would not stop. As the end approaches, the force would grow strong enough to overcome the gravity holding solar systems together. Planets would be ripped away from their stars, sent tumbling into the void. In the final terrible moments, the force would overwhelm the chemical bonds that hold molecules together. The planets, the stars, the cold stellar corpses all over it would be torn apart into a cloud of atoms. And then, in the very last fraction of a second, the dark energy would become so powerful that it would overwhelm the strong nuclear force itself. The atoms, the very building blocks of matter, would be torn apart. The fabric of reality itself would be shredded. Everything from the largest galaxy to the smallest particle would be ripped to pieces. The Big Freeze or the Big Rip, a slow, cold, quiet death or a fast, violent, total annihilation. We do not know which, if either, will be our ultimate fate. We simply do not know enough about the dark energy that controls our destiny. But what we do know is now. We know that we exist in a special fleeting moment in the life of the cosmos. We live in the stelliferous era, the starry eras. We are balanced for now in this brief warm interlude between the fire of the Big Bang and the ultimate cold end. The universe is not too young and hot. It is not too old and empty. It is just right. It is an era where the cosmos is rich with material, where stars are being born, where planets can form, and where on at least one small blue world consciousness has emerged and can look up at the sky. We are the universe's way of knowing itself, even if only for a moment. The cosmos had a beginning, and it will have an end. We are the lucky ones who get to exist in the middle in this warm, starry, beautiful age, able to look up and to wonder. And that perhaps makes this brief moment everything. Let that thought settle. The vastness of time, the cold of the future, and the small, precious living warmth of right now. We have journeyed so very far. Together we have pushed our imagination to the very edge of the cosmos. We have walked among the great superclusters, those islands of light in the cosmic ocean. We have witnessed the grand invisible architecture of the cosmic web, the immense filaments of galaxies stretching across billions of light years, separated by silent, unimaginable voids. We have spoken of forces that bend light and histories so long they dwarf our own. But after all this wandering, it is time to come home. Let us begin the journey back. We pull our gaze away from the edge of the observable universe past the ancient quasars. We fly back past the countless galaxies we will never visit, past our neighbours, like Andromeda, which is already hurtling toward us in a dance that will take billions of years to complete. We cross the dark, cold frontier of our own solar system, past the distant orbits of Pluto and the icy comets asleep in the dark. We pass the gas giants Jupiter and Saturn, majestic and indifferent, and the red speck of Mars. We are returning to a small, fragile blue and white world. We are returning to this room. We are returning to you. From the vastness of that cosmic web, our home is less than a single grain of sand. In the year 1990, the Voyager 1 spacecraft, after completing its grand tour of the outer planets, was about to leave our solar system forever. At the urging of the astronomer Carl Sagan, it turned its camera around one last time to take a final picture. From 4 billion miles away, our Earth appeared as a single tiny point of light. It was captured in a scattered ray of sunlight, almost invisible, like a mote of dust suspended in a sunbeam. Sagan called it the pale blue dot. Look at that picture. There is a profound loneliness in it. It shows us what we are, a tiny stage in a vast cosmic arena. The sheer terrifying emptiness of space is laid bare. We are isolated. In all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. But that loneliness is also a powerful lesson. On that single pixel, that one dot, is everyone you have ever loved, everyone you know, everyone you have ever heard of, every human being who ever was lived out their lives there. It is the aggregate of all our joy and all our suffering. Thousands of confident religions, ideologies, and economic doctrines. Every hero and every coward, every creator and every destroyer of civilization. Every king and every peasant, every young couple in love, every mother and father, every hopeful child, every saint and every sinner in the history of our species lived right there. All our wars, all our triumphs, all our imagined self-importance are challenged by this one distant image. It shows us that we are all in this together. It underscores our responsibility to deal more kindly with one another and to preserve and cherish this pale blue dot, the only home we have ever known. This perspective can be overwhelming. If we are so insignificant, what is the meaning of it all? If we are just a speck of dust, does anything we do matter? Does anything we do? Perhaps the meaning is this: we are the universe's way of knowing itself. Think about the journey that led to this moment. The universe began 13.8 billion years ago. In the first moments, there was no thought. There was no life. There was only energy which cooled to form the simplest atoms, mostly hydrogen and helium. The universe was for a very long time dark and unthinking. But then great clouds of that gas collapsed under their own gravity to form the first stars. In the furnaces of those stars, those simple atoms were fused together to create heavier elements. They created the carbon in your skin, the nitrogen in your DNA, the calcium in your bones, and the iron in your blood. When those massive stars died, they exploded in brilliant supernovae, scattering these new life-giving elements across the earth. We are all of us literally made of stardust. That stardust gathered, it formed new stars and new planets. On at least one of these planets, our planet, something truly remarkable happened. That stardust, governed by the laws of physics and chemistry, organized itself. It became life, and that life, over billions of years, evolved. It grew more complex. It developed fins, then legs, then wings, and on one branch of that tree of life, it developed a nervous system, and finally a brain capable of consciousness. That is us, you and I. We are the improbable result of 13.8 billion years of cosmic evolution. We are stardust that has woken up. We are the part of the universe that can look back at the rest of it. The cosmos was blind and silent, and then through us, it suddenly developed eyes to see its own beauty and a mind to comprehend its own vastness. The atoms in your body have been on an incredible journey. They have travelled across light years and survived the hearts of dying stars. And now they are assembled into you, and you have the profound, beautiful privilege of being able to wonder. You can look up at the night sky and understand, even in a small way, the science of the very stars you came from. This is our meaning. We are not separate from the cosmos. We are the cosmos. We are its senses. We are its consciousness. So as you lie here ready for sleep, remember what you are. The silence of space is not empty. It is not a void. It is a library. It is full of history, with the ancient light of distant galaxies travelling for eons just to land on your retina. It is full of light, the energy that powers our world and illuminates the faces of those we love. And it is full of possibility, the potential for new discoveries, new futures, and the enduring mystery of what else might be out there. You are not just an observer of this universe, you are a participant. You are a fundamental piece of it. In this quiet, peaceful moment in the darkness of your room, you're connected to all of it. The atoms that make up your hand are the same atoms that make up the most distant star. You're a part of this grand unfolding story. Good night. Sleep well, you conscious piece of stardust sleeping soundly tonight amidst the eternal silent dance of the galaxies.